This video is all about the reflection of sound waves. You guys have seen reflected waves before in your two-dimensional wave motion lesson. So you've seen how reflection works with water waves. All waves reflect more or less in the same manner. So all of the same rules apply. I'm not going to restart how waves reflect in general, but just focus on what it means for sound. So when a sound wave reflects, we tend to think of it as an echo. You've probably done that as a child when you went into a cliff edge somewhere and or just a valley or a gorge or someplace where you notice that when you say the odd word, it comes back to you and it sounds kind of neat. So that's essentially the reflected sound wave. Travels from your mouth, hits a surface, bounces back, hits your ear. And when you're a kid, you think it's kind of neat. Um, when you walk into a large empty room, you get a little bit of an echo, but it's not really clear or distinct. So that's mainly because the initial word that you say is overlapping and interfering with the actual reflected word. And so it doesn't quite sound like there's an actual echo. So for that reason, they usually, and by they, I mean, it's usually determined that you need about a 0.1 of a second difference between the word that was spoken versus the word that was reflected. So the echo, if you will, you need a little bit of a time delay between the two in order for that to really seem like an echo. So I have a little animation here that's kind of like gives you the rough idea. You can just look at the still picture if you want. If one person is speaking and somebody's listening, you're hearing sound from many different sources. You're hearing the original incident wave, so from the actual mouth of the or the speaker, if you will, of your sound system, if you have that, going straight from the source straight to your ear, and you will hear the reflected sound waves, as you can kind of see with all these lines going all over the place, reflecting off the wall, reflecting off the ground, reflecting off furniture or any other hard surface around you. So you're going to hear all those more or less at the same time, just not exactly the same time. And so when that happens, you get that reverberation. It just sounds like this, like it lingers a little bit. You would notice that a bit more if you walked into the gymnasium one day, if you got to school early and there was no one in the gymnasium. If you just walked in and started talking, you'd hear this reverberation a little bit more clearly. Um, so you might notice it in other places, like some spots in your house. I know in the stairwell and in my house, I can get some pretty clear, distinct reverberations if I stand on the third step, and then I can actually hear it. It sort of sounds neat. Other people say they get reverberations in the shower because you're basically in a tube where you have some kind of vinyl shower curtain, or maybe you just have one of those stand-up showers where you have hard doors where the sound is just going to bounce off the doors and basically have yourself your own little personal reverberation chamber where might make you sound nice. Sometimes that superposition of interfering reflected sound waves versus the incident sound waves might help cancel off the pitches that are not exactly in tune, or so I'm told. But that's one place where you might notice some reverberations. So graphically, I kind of found this just by doing a quick little Google search. The difference between an echo versus reverberation: an echo is a clear, distinct. You hear the original, you say the original word, and the echo comes a little bit later, and it's typically a little less intense because it had to travel a lot further, and that piggybacks on our intensity lesson the other day when it comes to the distance you are from the source and how it becomes quieter. Whereas reverberation, you can kind of see the overlapping of the original hello, and that's kind of visually, that's kind of what it sounds like. Maybe it doesn't linger as long, especially not in my classroom, but it does linger a little bit. If you ever get the chance, go visit an anechoic chamber. I know they have one at the U of S. It's a chamber where they cancel out all reverberations, all echoes. It's great for testing sound equipment or just trying to sort out mechanical resonance altogether. You can't see it too well, but there's a link here where a man walks you through an anechoic chamber. It's kind of neat. It's a 3D YouTube video, so that means you can click and drag and follow him as he walks around in the video. You'll definitely have to do that. It's neat. I won't click it here. I'll put that link down below. and actually watch it. It's like a 5-ish minute video, and it's pretty neat. Please listen to it. So how it gets used, people your age would probably have seen a fish finder if they go fishing at some point growing up, or maybe you hurt a bone or a ligament and you went into the doctor to get an ultrasound. That's typically how you might notice reflection of sound being used anywhere aside from an echo. So this image that I have here is with a big fishing boat, and it's using a fish finder, and it's just all some type of sonar device. Even ultrasound machines are basically sonar devices, and that of course stands for sound navigation and ranging. A little bit different than radar. This uses mechanical waves, so you need an actual medium like the air. Well, air doesn't work as well, but for instance, the water is a great medium for the sound waves to travel through. If we're talking about ultrasound, your tissues, your fat cells, your muscles, your bones are great things to use for sound waves to travel through. So basically a pulse is sent with a transducer. So that's kind of like a speaker. You get a pulse that's sent out, it hits something solid, it reflects back, and it gets picked up by the hydrophone. So you can use sound to figure out field of view, density, a little bit of porosity, if you will, as well. And the most important thing you can determine with it is the actual distance to the actual, in this case, bottom of the lake or ocean or whatever this diagram is of, right? Or of course, you can find the distance to the little school of fish that you have. So the hydrophone actually receives the echo. That's the main part. You can also tune the computer program that recognizes the echo to have different colors for different depths. And with that, you can kind of paint a picture of what's down below. So this is just a picture of a sunken ship based on probably the top of the ship right there is closer to the water surface than the bottom of the ship down here. So of course, this would be lighter colored. It gives you an idea without having to go diving down, because that would take a long time to dive around, look in the bottom of the water's floor to look for whatever it is that you're missing. So real quick example problem. Suppose you have a ship and it's anchored where the depth of the water is 120 meters, and they use an ultrasonic signal, so you wouldn't actually hear this one, but it's still part of sound, quote unquote, waves. And we send that ultrasonic signal to the bottom of the lake, and it returns in 0.16 seconds. So what is the speed of sound in water? So I drew a picture because often with physics, drawing pictures help. So not a very fancy boat, but that's what I drew. So we have the depth of the anchor. We're going to assume that there's no wind. If you've ever been in the boat and you put an anchor down, it's going to more or less make the anchor rope look like this. We're not going to do trig in this question. So we're just going to assume it goes straight down, it's holding the boat straight vertical, and we know the distance going down. So that's the big one. We know that the sound wave is going to travel down in the red, hit the bottom of the lake, and then, or the water, whatever wasn't defined, just whatever the water is, and then it's going to reflect in the blue. So it's going to travel that distance of 120 meters twice. The incident wave is going to go down, the reflected wave is going to go up. So that 0.160 seconds is actually the total time for the trip. So that includes the time there and the time back. We've only been given the distance going one way. So therefore we should make an adjustment. So the adjustment is, here's all my givens, but the main adjustment that we want to make is we have to divide our total time by 2. And that's mainly because we were only given the distance going down. The other thing we could do is multiply the distance by 2, but pick one or the other, don't do both. So I tend to divide my time in half whenever I'm doing a reflection problem, if I know my total time of the journey. So I've got my anchor depth, I've got the total time, I've now got the time to go one way going to the bottom of the water. So I have to find the speed of sound in water. So typically that would just be your straightforward grade 10 kinematics equation relating your speed to your distance divided by time. That's all speed really is. Even the units meters per second tells you take your distance, your length, if you will, divided by time. You know your length, 120 meters to 3 significant figures. And since we had 3 significant figures for your time, When you divide it by 2, just keep 3 significant figures, because 2 is not significant, it's just a factor. Do your mathematics. So 120 divided by 0.08 will give you pretty close to 1,500, if not exactly. And of course, because the number is 1,500, you can look at it as 1.5 times 1.50 times 10 to the 3 for the large number, or in my case, I tend to use prefixes because it makes the number look a lot neater. So 1.5 kilometers per second. Typically, your answer keys would probably default to a prefix. So when you're doing your practice problems, if you calculate something like 1,500, and you go, oh, I didn't get it right, the answer is 1.5. Do make sure you look at what units are in the answers, okay? So that's often a problem that students come to me afterwards and say, I keep getting it wrong. Well, check your units, okay? Other places you might see reflection of sound is if you watch sports, like specifically football, you'll see these guys standing around the end zone or just all around the place because they're trying to pick up the sounds of people getting crunched. So they are known as parabolic microphones. And again, if I fall back a few lessons to the two-dimensional waves, we talked about what happens when a wave hits a curved surface. So if it's a parabolic surface, it's going to all reflect, all the sound waves, all the water waves, all the waves in general are going to reflect to a single focal point. So since that is a well-known thing in physics, they found a low-tech way of capturing the sound of sports guys doing their sports things. Football, soccer, whatever the case may be. They just pick up the sound. All they have to do is just carry a little battery pack, put a microphone there, and they can record those sounds for TV or just for afterwards, for putting them into video games or whatever the case may be. You can also use, bird watchers like to use this stuff too, because again, it is low tech. Spies like to use this as well. You can use your imagination on where you would want to use a parabolic microphone. Amphitheaters rely on reflection of sound, so very often if you go into a big theater hall, they will have curved surfaces on their ceilings, specifically so that whatever's going on, whether it's the opera, a singer, or just a guest speaker, or whatever the case may be, all the sound gets reflected and pushed to all the members of the audience fairly evenly, so that every seat ideally is a good seat in the for the show. It's probably doesn't always work out that way, but that is the goal when they engineer the actual building. I've used to use this stuff in the oil field. You would actually stick some kind of a sound emitting tool into the well, and that will find you all sorts of things like well porosity, or in the case here, the tool that's going into this well right now. Well, I'm not totally certain what this tool is because I can't tell, it's just red. But what we used to do is we would put some tools into this little Christmas tree here, and we would check to see whether or not the casings were in a decent shape. And you can see as you look at the graph, you have smooth lines here, but then it gets all kind of rough every so many meters. And that just tells you where the collars are or where potential cracks are in either the casing or in the concrete behind the actual casing. They're also great for using reflection of sound to find out where the oil or gas is in another type of well. If it's an oil well or a gas well, typically sound travels a lot slower in a gas than it does in a solid or a liquid. So when you reach a gas, like in this pocket right here, the graph tends to separate. And usually when that happens, if you are owning the oil well and you see that, you're usually quite happy because that's a lot of money. A lot of gas in this case. And if you actually look at the distance separation between this point and this point, it's quite a few 100 feet. So that's usually a very profitable well. And that's, again, just using a simple tool like the reflection of sound. Other things, so the odd one or two of you guys might have had an ultrasound already. So this was just an animation pulled from Google of just somebody flexing their muscle. And they were just looking to detect the flow rates, and so that's what the blue and the red is. It's just showing whether or not the blood is flowing towards the screen, towards your face, or back into the screen. And it's just using sound to detect this, and the difference in depths of all the tissues will determine whether or not a lot of the sound gets reflected back, or only a little bit of the sound gets reflected back based on, again, I'm going to go back to an old lesson, whether you're moving from a fast medium to a slow medium, or if you'd rather a more dense medium to a less dense medium. So it's all about transmitting and reflecting of a wave, right? Some will go through, if you remember, if you send a crest and it goes into a denser medium, so denser medium, a trough will get reflected back, but a crest will definitely go into the new medium, right? And so what the ultrasound is actually detecting is whether or not it comes back. A simple way to think of it is whether or not it comes back as a trough, or whether or not it comes back as a crest, or whatnot. So that's the simple explanation. There's a bit more involved to figure out things like porosity and whatnot and densities, but the real simple is just basically that one-dimensional wave reflection that we talked about a few lessons ago. I'll just do one more math question real quick. So suppose a boy yells towards a cliff and hears his echo 3 seconds later. So here's a little cartoon man yelling, or a boy is yelling. His echo is reflected off this cliff's edge. How far away is this cliff? So we have the incident wave hitting the cliff's surface. We have the reflected wave coming back. It takes 3 seconds to do that. We don't know the distance. That's what we're trying to find out. We also don't know what the actual speed of sound is outside, but we do know that the temperature is 15 degrees Celsius. So from that, we can determine what the speed of sound is. So first off, we're going to use our basic kinematics equation. Distance is equal to speed times time. And if our temperature is 15 degrees Celsius, then we will use our speed of sound equation. So 331.4 meters per second plus 0.6 meters per second for every degree Celsius. And then we'll just have to plug in 15 into that when we get around to it. So 15 times 0.6 should be 9. So we should end up with 9 meters per second. The degrees Celsius cancels out. And then just add the two together. Now we have our speed of sound. So the last thing we want to do is figure out what our distance is. So knowing that our total time to go there and back with the sound is 3 seconds, we just want our sound going one way. So all we have to do is just recognize that the incident time would be Ti going to the wall, to the cliff's edge. The reflected time would be the blue one coming back. So since it's going to travel the exact same distance, we know that these two guys are the same time. So that we just have to divide our total time by 2. So it should just take 1.5 seconds to go one way for the sound wave. Plugging that into our distance of speed times time, you would take your 340.4 meters per second, multiply by 1.5, and you should get approximately 510.6 meters. Now, according to what I was given, I should just have 2 significant figures, so I would probably just round that up to 510 meters. So that's how far away this cliff's edge is, about half a kilometer. So I'm going to stop there because I could probably go on forever on this topic. Try the reflection of sound problems. Remember that if you're given the total time, to divide it by 2, because you don't want to, otherwise it's not going to work out for you. If you have any questions, just contact me, email me, or wait for the next day when I see you, whatever works best for you. Okay, have a good night.